We investigate the shoreline resistance and resilience associated to a transient disturbance on a sea breeze-dominated sandy beach. This picture corresponds to the artificial disturbance employed for this study. The term resilience was coined more than 150 years ago to describe the capability of steel to resist forces and withstand its deformation. Since then, the term was adopted different definitions depending on the discipline of its application. For the study of resilience, it is important to adopt some key terms. The term disturbance is known as a shock that induces a response which can be a pulse or a ramp. On the other hand, the perturbation is the effect of such action on the system's functionality. The resistance is defined as the system's capability to withstand a perturbation. Finally, the term resilience, which means rebounding, can be described from an engineering perspective as the ability to recover to a pre-disturbed state. However, another school of thinking relaxes this constraint and allows a change of state known as trajectory, where the functionality is preserved. A beach disturbance consisting on an impermeable groin made of plywood sheets was deployed for 24 hours. Beach morphology was surveyed with a high temporal resolution along 15 survey lines, covering the up and down drift sides of the temporary structure. A differential GPS was employed using real-time kinematics for conducting the topographic surveys. The alongshore distance between transects varies from 2 to 6 meters, with the highest resolution corresponding to those transects located close to the structure. The beach surveys were conducted every other hour for 24 hours. Furthermore, measurements continued after the structure removal, with the same 2-hour temporal resolution for 10 hours, and then were resumed with a lower temporal resolution until the beach was fully recovered. Intense winds associated with sea breeze events generated short-period oblique waves approaching from the northeast. The temporary structure was deployed during neap tide in order to decrease the influence of the tide on the effective length of the groin and hence restricting the swash zone width. The structure was deployed on the morning when wave conditions were mild. As the sea breeze wind increases, the alongshore transport becomes interrupted in the eastward side of the structure. The temporary groin was removed and the shoreline disturbance smoothed out during the following days until reaching the pre-disturbed condition after 144 hours. The shoreline resistance and resilience associated to the presence of the temporal groin can be evaluated by analyzing the resulting spatial and temporal functions. The first mode of variability, which represents more than 91% of the total variance, has been associated solely to the groin influence. The spatial function of the first mode describes the shoreline perturbation with positive and negative values associated to accretion and erosion at the updrift and downdrift side of the temporal groin. Furthermore, the temporal evolution shows an increase from 0 to a maximum value in the first 24 hours before structure removal. After the structure removal, it shows an evolution towards the initial condition, which is reached after 144 hours. Numerical simulations have been conducted by means of a newly proposed morphodynamic model named General Shoreline Beach, developed by the University of Salento. The GSB model was calibrated and verified with the field data to further investigate the beach resistance and resilience phenomena. Results suggest that resistance to the coastal structure decreases with increasing intensity of wave conditions, enhancing alongshore sediment transport. On the other hand, for a given wave height, the resilience to perturbation increases as a function of the alongshore diffusivity.